Hello everyone, my name is Chenga Liu and I am the team captain. Thank you for reviewing our project. We are the Solar Eagle from the Embry-Riddle Aeronautical University. We're presenting our solar energy system design with energy storage. The district that is assigned to us is the New Mexico State University in Las Cruces.
Hi there, I'm Ben. I'm a member of the design team. Basically what we came up with was a PV system that would spread over 8 of the 10 buildings we were given loads for. These buildings combine in total generate 2.2 megawatts of power. We have an additional 6.7 megawatts spread over 14 acres of the open field. And in that same field, we have our 8.7 megawatt, 32.1 megawatt hour battery system spread over half an acre. For the Horseshoe design, we came up with a series of solar-powered benches that would allow the students to reap the benefits of these solar upgrades while enjoying the open space.
Hello, I'm Raymond Miller, and I was the main part in the system design. And so what we had was we had provided 10 building loads, and we decided to put 8 rooftop subsystems on the building, along with the open area in the, there's 29 acres, but we used about 14 acres. And with this, and the location of Las Cruces, New Mexico, it's very favorable for solar resource, and using NREL maps and Aurora, we were provided with the irradiance and shading analysis. So we had placement on rooftops and put them in places where they would be most effective and see less shading over the project life. And with this, we accounted the also battery storage in the solar field that would be peak shaving throughout the evening and nighttime loads. And with this, it's to avoid high demand charges throughout the project life. Next slide. We chose the Panasonic HIT N330 DC panels, which are rated 330 watts and have a 20% module efficiency compared to commercial solar panels that are usually 15 to 18% efficient. Our panel has a low power temp coefficient, allowing the panels to remain effective and efficient during high temperatures that New Mexico incorporates. And with that, we put that into our derating factor along with weather conditions and other variables for our total derating of the system. And we used about 26,700 modules to meet the daytime loads throughout the project life. Next slide. Along with this, we chose 2 batteries from the same manufacturer. It was the EOS 100-300 and the EOS Aurora 1000-4000. These are zinc hybrid cathode batteries with high energy. We chose these because of their high energy capacity and storage capacity, as they will be peak shaving throughout the night. So we needed something that has enough capacity to last through the night and then recharge in the morning. And each battery is built for a specific building. So we have 27 100-300s and 6 1000-4000 batteries, and they're all placed in close proximity to the geothermal substation. With this, our rooftop subsystems contain panels and string lengths. It's 17 to 19 panels in 1 string length, and they're connected to a Selectria XGI 1500 inverter with a DC to AC ratio conversion of about 1.47. And each inverter can handle about 170 kilowatts of operating PV power. And this is useful because most of our subsystems are about 170 or a lot more. So we use this, and then these inverters are connected to the distributed panel on the building and then connected to the meter. And then with this, the remaining daytime loads are received from the open area. And in addition, we added 2 standalone systems, solar benches and solar stands in the Horseshoe. And this is just for people to utilize solar energy with their laptops, phones, or other electrical devices, and just have a feel for solar energy and more awareness.
I am Adil Harbi, and this section focuses on modeling the PV and the storage system on OpenDSS. Next slide. Starting with the rooftop PV system, the map here shows some of the building we use within the campus, and the blue color represents the building with the load and a PV system on it. And each of these PV systems is directly connected to the high voltage site of the transformer associated with each building. And you can notice that Brilliant has an inverter control with the volt var mode, and that's to mitigate the voltage violation on Brilliant transformer. And also there are two PV systems, one installed in Banham Center and the other is installed on Milton. And they're both connected to the high voltage side of the transformer associated with Corbett building. Next slide. The remaining power is coming from an open area that is located beside the substation. And this open area has a PV system of 6.7 megawatt and a storage system of a total 8.7 megawatt with energy capacity of 32.1 megawatt hour. And they both are connected to the substation transformer. Next slide. Here is a result or some of the results of a 6-month simulation in OpenDSS. On the left hand, the graph shows the production of one of the PV system, and on the right hand, the graph shows the battery charge and discharge power. The negative value means that the battery is discharging, and the positive value means that the battery is charging. And the table here shows a comparison between the circuit before and after adding the PV and the battery system in terms of voltage violations. And you can notice that the modified circuit or the circuit with the PV and the battery system has less violation than the original circuit, which was our goal. Next slide.
I'm Kristen Holman, and I'll be talking about the finances of the project. So in order to determine if our system has a positive economic benefit, we had to see if the payback period was less than 20 years. In order to do this, we used NREL's SAM and the NBA heat spring model. We had to include the indirect capital costs that are listed below. Next slide. For our financial model, we chose a partnership flip, and along with that, we had to include incentives. We were able to include the federal ITC, Maker's Appreciation, the Sustainable Building Credit, and New Mexico State Tax Credit. We also had to model the balance of system elements such as the racking, wiring, and grounding equipment. New Mexico State's utility rate was also important. Right now, they currently receive a weighted average of 3.8 cents per kilowatt hour. And for our PPA price, we chose 3.7 cents, which is slightly lower, to get a net present value of customer savings of 16 million. This pie graph shows the initial PV system costs. In gray is the module cost at $7 million. And in light blue is the balance of system elements cost at $3 million. This adds to a total PV system cost of 16 million, with the cash equity investor having a net present value of 5 million and an IRR of 5%, and the tax equity investor having a net present value of 3 million and an IRR of 11.75%. With our battery energy storage, the cost will be $16 million as well, including construction and other costs. The replacement will happen at year 15, and this gives a net present value of $34 million. Next slide. This graph is a graph showing the cash flow of the combined PV and battery. It shows the payback period at year 6.5 and the battery replacement at year 15.
Hi, this is Chinga again, and I'll be talking about the development plan as well as the construction timeline. So here is the breakdown of the building and land utilization. The table on the right shows the number of panels and their area utilization on each building rooftops and the open area. Some examples for buildings that we did not put PV panels on the roofs are Gardner Hall, which has a power line limitation. Hernandez Hall and Jet Hall has an unusual roof obstructions. Here's a campus site plan. The orange buildings represents the buildings that are receiving energy, but we were not given the load. And the green buildings represents the buildings with solar panels, but we were not given the load. And last but not least, the blue ones are the energy receiving buildings with the solar panels on them. So the next one is the field site plan. And the battery, as you can see, is located in the corner of the field, and we have fencing around the batteries as well as the solar panels. The picture on the right shows the number of batteries that are dedicated to each building. Next, we have the Horseshoe site plan. For the Horseshoe area, there are 3 solar benches and 1 solar charging stand. Before any constructions, some permits need to be applied ahead of time. First, we have the state building and re-roof permit for the buildings on campus. Next, we have the special permit for the field due to the change of more than 15% of land utilization. The electrical permit is for the PV system as well as the power line. And last but not least, the fence permit is for the PV system and the batteries that are located in the field. This is the estimate construction timeline, which is within 6 months. And most of the construction will be done during summer break when there's a minimum amount of students on campus.
Ben again, and I'll be leading you through some of the Innovation Center project. Next slide. All right, so what we ended up with was a PV system that was capable of meeting all daytime loads experienced by the buildings we were given, and a battery system that's capable of meeting all peak demand loads in order to reduce peak demand charges on the customer. As an extra bonus, we project that there will be a slight reduction in the HVAC cooling loads due to the shading from the rooftop panels. However, finally, in order to make sure that we'll be able to use the battery to its full potential, the system is going to be charged from the grid rather than any excess solar generation. Next slide. With that in mind, the daily routine for the system gets broken down like this. From sunrise to sunset, all school loads will be met by the PV system. From 8 a.m. to 12 p.m., the battery will be charged from the grid. And if at any point during the day, a peak load line crosses our generation curve, that load will be met by the battery, provided the charging cycle has been complete. And last, at sunset or at the end of that peak demand period, until the battery is needed again, it will go into standby mode and the school loads will be met by the grid. The optimization strategy. So how did we get here? With any design, there is more than one iteration to get to the final version. The path we followed was very similar to this one. We evaluated the provided electrical loads, we decided on a storage strategy for our battery, compiled a candidate panel and battery list, updated the battery, and then based on that, designed our battery plus PV configuration. From there, we evaluated our electrical performance and any financial or site plan limitations. If we encountered a problem with any of those steps, we looped right back around to the design and started fresh. In the grand scheme of our optimization process, we went through 3 major design iterations. In September, we started with a space-defined system. We were just trying to get as many panels on campus as possible for maximum generation. Once we integrated our battery system, our design was changed to try and use that oversized PV system to charge the battery as a load shifting device. However, after we spoke to some industry experts, we realized it would be much more efficient to charge the battery from the grid rather than the excess panels. So we elected to reduce our total panel count to supply the buildings that we were given loads for. Next slide, please. And then this slide just gives a summary of how the various design tools were used and at what point in the design process.
So in conclusion, we have 2 subsystems. We have rooftop subsystems with panels at 0 degrees tilt, and then we have ground mounted systems at 32 degrees tilt, and these are all to provide for daytime loads, attached with a peak shaving storage system to avoid high demand charges. And with this system, we have a payback period of about 6.5 to 7 years. And it's cost effective, saving the campus at least $250,000 a year for 20 years, as it's a reliable project to distribute solar power to all loads provided. And then this design is resilient despite variable weather conditions provided by Las Cruces, New Mexico. And if you go to our next slide, we have our references that we've used throughout the project. And with that, I would like to open for questions.